In this lesson, we're going to talk about specular highlighting. So specular highlighting simulates glossy surfaces. So a very common, very popular model for simulating specular highlighting is the Blin-Fong model, named for two fellows from the University of Utah. So Blin-Fong looks like this. Let's look at the vertex shader here real quick and show you that it's the same as the last with one minor addition, right? So we're passing the worldview projection matrix as before, the world matrix as before. The light direction, we're going to use directional lighting again. Each vertex is going to have a position, a texture coordinate, and a normal. All of that data is being passed through just as it was in the last demonstration. The difference now is I'm also passing the world position. So in addition to computing the position into homogeneous space, I'm also taking that same object position and transforming it into a world space. And I'm passing that as an output vector of vec3 into the world position member of the VS output struct. So now why am I doing that? Well, because as you'll see in the fragment shader, our specular model depends on the direction of the viewer. So the viewer being the camera. And you can simulate this yourself. If your desk is shiny, like mine is here, you can actually move your head around. And as you move your head around, notice how the highlight, that shininess, moves with you. And the way that we'll discuss that is as the view direction. And how do we compute the view direction? We'll compute the view direction as the camera position minus the world position. Remember that I can take two position vectors, the camera position in world space, and the world position that we just passed in from the vertex shader. And we'll subtract those two, and that gives us a direction vector where the arrow, right, is coming from the camera to the world's position. So we want that view direction. So now what we can do is we're going to compute a half vector. And that half vector is the addition of the light direction and this view direction. And this is how the Blin-Fong model actually looks. Blin-Fong model says we're going to create this half vector, that direction vector plus the view direction. And notice that I'm normalizing it here just to be sure that this doesn't go past unit length. And now I'm going to do the dot product between the normal vector and the half vector. So using the GLSL intrinsic dot, I'm going to dot the normal vector and the half vector. That data is what I'm going to raise to a specular power. So if you see this line down here for specularity, right? Specularity is n dot h, so the normal vector dotted with a half vector raised to the power of n, where n is a specular power. So notice that I'm passing in a specular power uniform of type float and a specular color uniform that's of type vec4. So this specular color, it just gives artists another knob to tweak, right? It allows us to change the specular color independent of the light's color, independent of the ambient color. If you don't want to do that, if you want to make that map directly to the light's color, so be it. So I've got this extra specular color in here, and you'll see how I'm employing that here in just 1 second. This POW, that's the GLSL intrinsic POW, which gives me the power of. So I'm raising this side to the power of this. So I'm clamping the n.h, the dot product between the normal vector and the half vector, between 0 and 1. So no negative values. If that dot product is behind the light, then there won't be any specularity. So if the surface is facing in the opposite direction of the light, or if it's perpendicular to the light, therefore it's 0, then I won't see any specular. That's a specular highlight that's just going to apply when the light is facing the surface, at least between 0 and 90 degrees. So I'm clamping that. I'm getting a value 0 to 1 that I'm raising to a specular power. And the specular power is what you'll pass in from the CPU side. Now I'm multiplying that by the specular color.RGB. So that's where the color of the specular light comes into play. What's this other stuff? What's this min and sampled color.W? I want to mention the term at least as a specular map or a gloss map. And we're storing this specular map inside of the W channel, the alpha channel of the color texture. I'm going to come back to that, but bear with me for just a second while we show you the demo, and then I'll show you the specular map and how that min value applies. So finally, you can see that I haven't changed anything about how I sample the texture, how I compute the ambient and diffuse terms, and again, this is additive. So I take the ambient plus the diffuse plus the specular, and that gives me the RGB values for the final color of each fragment. All right, so now let's go to the CPU side, look at the Blin-Fong demo.h, and notice that I've got a light rotation rate, that's for my directional light. I also have a light modulation rate, and that's going to allow me to change how that light is affected over time. So when I want to change the intensity of my specular light or my ambient light or my diffuse light, I can do that with a light modulation rate. But I've got the same stuff that I had before. I have a directional light, ambient light, color texture, etc. But now I've got two new variables called specular color and specular power. So the specular color and specular power is exactly what we're going to put into the inputs as the shader. But now you're going to notice something else, that maybe something jumps out at you right now. And I'll pull up the previous lesson so that you can compare these right now. If we look at the diffuse lighting demo.h, I also had all of these GL ints for worldview projection location. And I had another one for ambient color location and world location and light color location and light direction location. So those are all gone now. They're gone because I've refactored the shader program into a more extensible system. So if we look at our mShader program, it's no longer of type shader program. Now it's actually of type blend Phong effect. And if I look at blend Phong effect, that's this class right down here. If I look at, let me collapse that. If I look at blend Phong effect here in shader programs, it's actually inheriting now from shader program. And it's added some strange looking syntax, but bear with me and I'll show you what this stuff means and how it's used. This is just a way to modularize some of this code so that I don't have to rewrite the same code over and over and over again. Instead, I can create effect classes that wrap specific shaders. And notice that the shader that I'm wrapping now, if you can imagine the shader variable declaration, this macro does something that exposes the vertex shader's world view projection and world and light direction. We'll see that, world view projection and world and light direction. If I look at the fragment shader for blend Phong, I've got ambient color and light color and camera position, specular color and specular power. So there's ambient color, light color, camera position, specular color, and spec power. Now you'll see that macro actually does. I'm not going to spend a lot of time talking about the macro use here. You can please explore this on your own. But what this is really doing is exposing these in just a simple step here, shader variable declaration. It exposes variables whose name is mVariable worldview projection. It's building a data type or a class member of type variable, which is a new data type that you haven't seen yet. Now that variable data type looks like this. It has a shader program reference, and this is that location. That location that we previously had is now stored inside of a class called variable. And that variable class can be reused over and over and over again. And if we combine a whole bunch of variables into an effect that derives from a shader program, well, now all of a sudden I can reuse that whole set of variables from one application to another without having to redeclare all of that code. So that's the whole point here. Notice there's a name that's associated with that. Well, that's that string name that we use for the lookup, right? And that name gets populated by that declaration. So that name is actually this string right here. Whatever this string is what the variable mName is going to amount to be. The other strange little syntax, and I was inspired by the IOStream cout, if you ever used cout or cin, and you look at the arrow operator, that's kind of the inspiration behind this syntax. This is just syntactical sugar to, and if I go look at, see my variable implementation. And so here's the variable implementation. And notice that the first thing that the constructor is doing from the name that you pass in, it's calling get GL uniform location. That's the same call that you're familiar with already, but now it's encapsulated inside of a class. And what are all these arrow operators doing? These angle bracket operators? Well, they're calling GL uniform matrix F4V if this was a matrix that was being passed in. Or if this was a vec4, then it's calling GL uniform 4FV. Or if it was a vec3, 3FV, and so on. If it was a single float, then it's GL uniform 1F. If it was a single integer, then GL uniform 1I. Now, these are the same calls that you've been making all along. We look back again at the implementation of diffuse lighting demo. Look at the draw call. We can see that the draw call has all of those calls. Well, I want to refactor that so that it doesn't look quite so hairy. And that's what lesson 5.3 is doing now with our blend Phong demo. Let's look at the implementation of our blend Phong demo. Gone are all of those strange looking calls here, that, not strange looking, pardon me, but gone are all of those explicit calls to GL uniform matrix 4FV or 3FV. And instead, we have exposed through our shader program, our explicit blend Phong effect shader program, our derivation of the shader program. We have accessors for the specific variables. So now we can access them at compile time. We know that they should be there. And that arrow syntax allows me to just pipe in, as if it were a cout stream, lets us pass in various data types. And all the different data types that we want to support can be expended through the variable data type, right? We can just keep adding operator arrows in order to overload that over and over again. So let's back up a second. There's something else. All right, this is the diffuse lighting shader. Something else that the diffuse lighting demo application did, right, is it did these explicit calls to get GL uniform location. Well, now in our blend fog demo, let's go to our blend fog demo as implementation. All of that's gone, and it's replaced specifically with our instantiation of our, let's pull this up, our instantiation of our blend fog effect class, this mShader program. When I call build program on it, I then have to call shader program initialize. And notice that I'm doing this initialize here after I'm calling glgen vertex array object. So I'm building the vertex array object first because I want to cache the locations, all of the locations that I'm concerned with, right? And also inside of that shader program, let me show you something else that it's doing. You're not seeing the input layouts either, right? So along with the subtraction of this content explicitly, it's now done implicitly. Also gone is the manual configuration, at least inside of each one of your demos, the manual configuration of the input layout. So where does that data gone? So let's go back to our shader program's initialize method and look at what the initialize method is doing here. The initialize method is calling this shader variable instantiate. So what this macro is doing is then, I'll go pull up the macro code here, is then actually building on the heap the variable associated with that class member, pushing it back to a list of variables and into a map, right? So it's doing the instantiation of the specific variable. And remember that when it did that instantiation, it did the GL uniform lookup, the GL uniform location call. Now, additionally, inside of the initialize method is where all the vertex attribute pointers are set up. So the layout is set up here rather than delegating that to the application every time. So for every time we want to use this effect, that work is now encapsulated inside of the initialize call to the specific effect. If we go back to the blend fog demo, I'm calling mShaderProgram.createVertexBuffer, and I no longer have a local createVertexBuffer method here. Instead, it's encapsulated with the specific shader program. Now, why do that? Well, because the shader is what dictates what data needs to be in the vertex buffer. Remember, the shader is what's dictating the layout, and hence what data needs to be provided by any vertices that are being passed into the shader. So it's only natural then that an extension like this include the ability to create a vertex buffer. Now, still inside of the mesh, I'm still not doing the index buffer here. And why not? Well, because there's only one type of index buffer. We can have lots of different types of vertex buffers. Those vertex buffers are specific to the data that the shader requires. Okay, so that really simplifies our code here. So all we're doing now is building the shader, loading the model, creating the vertex buffer, not by creating that code ourselves or copying it and pasting it, but rather than delegating that code off to the shader program, creating the index buffer for the mesh, loading a texture, and then doing the VAO setup just with these simple calls, right? Now it's glgen vertex array objects, and then initialize the shader passing in that VAO. Finally, we're going to instantiate the ambient light, the directional light, and another directional proxy model. And this time around, we've got a new update inside of the update method, which is update specular light. Let's take a look at that real quick. So the update specular light, it also has intensity. We use the home and end keys for the directional light. We're going to use the insert and delete keys to update the specular intensity, specifically of the specular light. And we're using, again, that uniform intensity, so it's going to be some shade of gray. And then we're also specifying the specular power with the O and the P keys. So as you press O and P, then those lights are being updated based on the elapsed time and some light modulation rate. So what this is saying is that it'll go to a value of 255. So 0 to 255 is its min and max. So its max is UCare max 255, and I'm going to do that in 1 second. If I held down the O key, it would go to 255 in 1 second. And if I held down the P key, it would go back down to 0 in 1 second. So let's go back to our draw method. Let's look at how our draw method is shaping up. So we had the same calls to rebind our vertex array object, our vertex and index buffers. Now we've got another method here for shader program use. Instead of explicitly calling GL use program, now we're simply calling GL shader program.use. All that does is just encapsulates GL use program. And now we're doing that syntactical sugar to specify inputs into our shader, right? Inputs into our shader coming from the world matrix, the ambient lights color, the directional lights color. This is new. This is the camera position, right? And the specular color and specular power. We're binding a color texture, and then we're doing the draw call just as we did before. So let's look at the output. All right, so here's our blend Phong effect. That's a specular highlight right there in the middle. And I can make it smaller or bigger. I'm pressing the O and the P keys, right? So I can make it a really, really bright highlight, or I can make it a very, very, very narrow highlight. That's affected by not only the directional light, so where's the direction of the directional light, but also notice how that's moving as I move around the sphere. That's that view direction stuff. Something else that I want to point out, and this comes to the specular map, that spec map or gloss map that I was talking about. For a model like the world, the glossy parts of the world will probably be the water, and the diffuse parts would be the land. So notice what's going to happen here. As I change my directional light, there's no specular or very, very little specular when I go over the land. Well, what's that all about? Well, that's what that specular map is. So notice that as I transition from the water to the land, I have specular highlight on the water, no specular highlight on the land. Now that came from that specular map little comment inside of the fragment shaders. Let's take a look at what that is. So this is the blend Phong model, n.h raised to the power of n. But now what I'm doing is taking that n.h raised to the power of n, that specular model, and I'm taking the minimum value of it and whatever was stored in the fourth channel, the alpha channel or the W channel. I'm specifying W here so that you're not confused that this is actually being used as opacity, because it's not being used as alpha. What's it being used for? It's being used for a specular map. It limits how much specularity we can have at that particular pixel on a pixel by pixel basis. It gives that an artist input into that process. So let's look at the spec map for the Earth. This is the specular map for the Earth. Everywhere that's white, and this is the simplest one you can dream up, right? It's just everywhere that's white is no limitation, and everywhere there's black, that means no specularity. Clearly, this is grayscale. This could be a shade of gray. But just for demonstration purposes, everywhere that's black is on land, and therefore there's no specular highlight that will be displayed there, and everywhere on water is full specular. And that's what that min value is all about. Now, clearly, if we were using alpha, if we really were using transparency in our texture, then we couldn't overload, we couldn't use that fourth channel inside of the texture for specular map. We would have to supply a separate spec map. No problem at all. I'm doing it here just for convenience. I don't have to load two different textures in my code and pass the shader to be sampled in two different places and two different instructions. All right, in the next lesson, we're going to talk about point lights.